Hello and welcome to the second presentation in the Hydrostatics series. In the first presentation we considered basic definitions, terminology and units associated with hydrostatic analysis. We defined various densities and undertook some calculations to determine the weights of fluids in various storage containers. In this second presentation we're now going to consider hydrostatic pressure, in other words pressure P, due to the weight of fluid of constant density. In this presentation we will define and use the formula P is equal to rho GH. It's a very standard formula used within hydrostatic analysis. It is encouraged that you've seen the previous introductory presentation before reviewing this presentation. And here's the presentation overview. We commence with an introduction where we derive the formula for pressure P due to the weight of liquid of constant density. This formula is P is equal to rho GH. We then state various definitions. Firstly, we define atmospheric pressure, denoted as P suffix at. We show how to calculate what we initially term as total pressure, which is the atmospheric pressure plus the pressure due to the weight of the fluid. We define a vacuum and gauge pressure, which is the pressure commonly measured and used by engineers. And then we define absolute pressure, restating the equation. An absolute, or what was termed total pressure initially, P, is again the atmospheric pressure plus the rho GH. You need to be very clear about the difference between gauge pressures and absolute pressures. Then we consider exercises 8 to 14 from our workbook. Basically we'll be using the above formulae to calculate various pressures. In some exercises we'll transpose the equations, for example to find the head of the fluid. Unless stated otherwise, we'll be calculating gauge pressures. There are full work solutions to all the exercises included in the presentation. Finally, I'll leave you with some questions, 1 to 7 from our workbook. The majority of these questions are based around the exercises, just slightly more contextualised in places, although question 6 is particularly difficult, so I've outlined the steps in the solution to question 6. And for reference, here are the approximate start times related to the various sections within the presentation, hopefully to aid your ease of access through the presentation. Let's consider pressure in a liquid due to the self-weight of the liquid. If we consider the vertical tube of liquid shown in figure 7, here's figure 7, here's the vertical tube of liquid here. It has a height h and a uniform area, capital A, at the base of the tank. The density is symbol rho. The total mass of the liquid column can be calculated from the formula of mass is equal to density times volume. So in symbol form, M is equal to rho, the mass density, multiplied by the cross-sectional area of the column, multiplied by height h of the liquid column. So essentially we can actually calculate the pressure P at depth h, in other words at the base of the tank in this case. So consider our formula, P is equal to the force at the base of the tank, which is basically the weight of the column of water, divided by the area of the base. Now remember that weight force is mass times gravitational acceleration. So to calculate the weight of the column, that's going to be mass multiplied by gravitational acceleration. Above we've already calculated the mass, it's rho AH. Multiply that by the gravitational acceleration g and divide by the area of the base A. We can calculate the formula for pressure. Essentially the pressure is equal to rho GH. Just notice here that the area on the top line cancels with the area on the bottom line to leave us the rho GH. And here's a slightly more detailed overview for determining the pressure P due to the weight of a liquid of constant density. So from P is equal to the weight force divided by the cross-sectional area. Weight force can be written as mass multiplied by gravitational acceleration. Cross-sectional area is capital A here. Multiplying the density of our liquid by its volume calculates the mass. Mass times G, still divided by the area. Mass density times volume can be written as mass density multiplied by cross-section area times the height, because the volume V of a prismatic section is the area of the base times the height. Area of the base times the height. And now we can clearly see the cross-sectional area in the numerator cancels with the cross-sectional area in the denominator. Thus we derive the equation P is equal to rho GH. So as the depth of the fluid increases, so does the hydrostatic pressure. Pressure distribution increases linearly with increasing depth. Depth is labelled H in our diagram. Let's consider atmospheric pressure. The Earth is surrounded by an atmosphere that's many miles high. The pressure due to this atmosphere at the Earth's surface depends upon the head of air above the surface. Note that head relates to the height of a vertical column of fluid and used to determine hydrostatic pressure. Atmospheric pressure at sea level is approximately 101.3 kilonewtons per meter squared. That's approximately 0.1 megapascals. That's equivalent to a head of water of 10.35 meters, or a head of 760 millimeters of mercury. And the pressure decreases with altitude. And of course, from our previous presentation, 0.1 megapascals is the same as 10 to the 5 pascals, which is equivalent to 1 bar. So in general, atmospheric pressure is assumed to be 1 bar. And this is the justification for engineers using a non-standard unit for pressure. The bar is not an SI unit, but because it equates to atmospheric pressure, it's useful for engineers to refer to. Pressure in a liquid due to self-weight continued. So figure 7 on the previous slide showed the vertical variation of pressure with depth in an open tank of liquid. Again, here's figure 7 for reference, and here's the variation in pressure from the free surface to the bottom of the tank. So larger pressure at the base of the tank than at the free surface of the liquid. So the pressure in a liquid due to self-weight is proportional to the depth labelled H here on figure 7, below the free surface OO, free surface labelled OO here. So within fluid mechanics, height H is sometimes termed the static pressure head, simply the head of fluid, and it's used by engineers as a measure of the pressure. So if atmospheric pressure acting on the free surface of liquid is denoted as P suffix AT, shown in figure 8. Figure 8, here's the atmospheric pressure acting on the free surface. Then the total pressure, denoted P, at depth H in the liquid is given by the following formula, where P is the total pressure, P at is the atmospheric pressure, shown here on the diagram, and the rho GH is the varying pressure here due to the weight of the fluid. You'll see in a moment what I refer to as total pressure on this slide is actually termed absolute pressure. Example 3. We're asked to calculate the pressure at the bottom of a 10 meter deep water tank if the atmospheric pressure is 1 bar, and we can assume the density of water to be 1000 kilograms per meter cubed. I'd encourage you to stop the presentation and attempt example 3. Here's the formula you will need to use to calculate the pressure at the base of the tank. but I'll show you the full work solution on the following slide. So example 3, here's the solution. Extracting the information from the question. The density of water is given as 1,000 kilograms per meter cubed. So that's the value of rho here. The height of the water tank is 10 meters. Height of water here, h, is 10 meters. So to calculate the maximum pressure, P at the base of the tank, this location here, we need to add the atmospheric pressure, P at, to the pressure due to the weight of the fluid, that's the rho GH. We're given in the question that the atmospheric pressure is 1 bar, so that's a 10 to the 5 pascals here. We add to that the rho GH, rho is 1,000 kilograms per meter cubed. We always assume G to be 9.81 meters per second squared, and the height H here is 10 meters. So that evaluates to a pressure of 198.1 kilopascals, and that's equivalent to 1.98 bar. Let's consider some definitions here. A vacuum. So a perfect vacuum is completely empty space, and thus the pressure in a vacuum is 0. Gauge pressure. This is the pressure that's indicated above that due to atmospheric pressure. Gauge pressure can be positive or negative, depending on whether it is above or below the atmospheric pressure. Pressure measurement devices, in other words pressure gauges, often do so by measuring pressure relative to the ambient, that's the room atmospheric pressure. So thus these pressure gauges register gauge pressure. It should be noted that when engineers are discussing pressures or undertaking calculations for pressures, it is usually gauge pressure they are referring to or calculating. Let's consider absolute pressure, and we'll refer to figure 9 here. This is figure 9. So absolute pressure is the intensity of pressure measured above absolute zero. As we said on the previous slide, that's a complete vacuum. So on this diagram here in figure 9, absolute zero commences from a complete vacuum. So this is 0 absolute pressure. Atmospheric pressure would be 1 bar absolute. We know that atmospheric pressure is 1 bar, so that's considered to be 1 bar absolute. If we consider gauge pressures, then gauge pressure commences from the atmospheric pressure. So we have positive gauge pressures above atmospheric pressure and negative gauge pressures below atmospheric pressure. So atmospheric pressure in terms of gauge pressure would be 0 bar gauge, assuming our pressures are stated in bar here. That of course means that a vacuum would actually be negative 1 bar gauge. Indeed, gauge pressures below atmospheric pressure are often termed vacuum pressures. If we consider the pressure at position B here on our diagram, we would have a positive absolute pressure, PB, but we'd have a negative gauge pressure, PBG, because we're below atmospheric pressure. If we consider pressure at position A on our diagram, we would have a positive absolute pressure, PA, and now a positive gauge pressure, PAG. So I'm not sure how useful that diagram is to illustrate the difference between absolute pressure and gauge pressure, but certainly we need to be aware of the difference between the two types of pressures. But in industry, most pressures that are measured are usually gauge pressure. Exercise 8, part A, is a car tire pressure stated at 200 kilopascals an absolute pressure or a gauge pressure? I'll let you consider that question. And part B, an aircraft fuselage test article is tested hydrostatically to an internal pressure of 0.17 megapascals. What would be the absolute internal pressure in bar? I'd encourage you to start the presentation and think through exercise 8 for yourself. but I'll show you the answers on the following slide. Exercise 8, solution. So part A is the car tyre pressure, an absolute or gauge pressure. The tyre pressure is a gauge pressure. It measures the pressure inside the tyre above atmospheric pressure. When you open the valve of the tyre, air is forced out because of the difference in pressure between the inside the tyre and the outside atmospheric pressure. Part B, related to the aircraft fuselage test pressure. The internal test pressure PI is 0.17 megapascals. That is a gauge pressure. That's equivalent to 1.7 bar gauge. So the absolute pressure, P-abs here, is the internal test pressure added to the atmospheric pressure. So the internal test pressure is 0.17 megapascals added to the atmospheric pressure of 1 bar or 0.1 megapascals. So the total absolute pressure is 0.27 megapascals, which is equivalent to 2.7 bar. It's exercise 9 here. So taking atmospheric pressure as 101,325,000 newtons per meter squared, we're asked to convert the following gauge pressures into absolute pressures, stating the answers in kilopascals. So the first pressure is 400 kilonewtons per meter squared. Second pressure is 20 meganewtons per meter squared. And the third pressure is 5,000 pascals. Answers shown in the bracket here. I encourage you to stop the presentation and attempt exercise 9, but I'll show you the answers on the following slide. So exercise 9, here's a solution. So parts A, B and C are solved using this equation where the absolute pressure is equal to the gauge pressure stated added to the atmospheric pressure given in the question. I'll let you review these solutions at your own pace. Exercise 10. The container shown is filled with water having a density of 1000 kilograms per meter cubed. We're asked to find the gauge pressure due to the water at a depth of 50 millimeters below the surface. So here's our container of water. Here's the position 50 millimeters below the surface of the water. Remember from our previous work that the pressure distribution varies linearly from the free surface as the depth of the fluid increases. So I'd encourage you now to start the presentation and attempt exercise 10. The answer is shown in the bracket here. I'll show you the solution on the following slide. So exercise 10, here's the solution. Essentially it's a question of applying the ρgh formula to find the pressure. Just be careful that the height is converted into meters, because our density is given in terms of meters cubed and the acceleration due to gravity is 9.81 meters per second squared. Thus we must have the height h in meters. I'll let you review the solution at your own pace. Exercise 11. A tank contains water to a depth of 600 millimeters. We're asked to calculate the water pressure A at a depth of 350 millimeters from the surface and B at the base of the tank. Again, we're allowed to assume the density of water is 1000 kilograms per meter cubed. They've also stated the gravitational acceleration here for reference. Answer to part A of the question and part B of the question shown in the bracket. Again, I would encourage you to start the presentation and answer exercise 11. Full solutions shown on the following slide. Exercise 11, here's a solution. I'll let you review this solution at your own pace. Again, it's a question of using the pressure is equal to ρgh formula. But remember to convert the heights that were given in millimeters into meters. Exercise 12. A storage tank contains petrol to a height of 4.7 meters. If the pressure at the base of the tank is 32.3 kilopascals, we're asked to determine the density of the petrol, again assuming gravitational acceleration is 9.81 meters per second squared. Density of the petrol shown in the bracket here. I suggest you attempt exercise 12, but I'll show the full solution on the following slide. Exercise 12, here's the solution. Again, we're referring to the formula P is equal to rho GH, but this time we need to transpose the equation because the question requires us to find the density of the petrol. So rearranging for mass density rho, we simply divide both sides by GH, so that becomes rho is equal to P divided by GH. We insert the values and the density of the petrol is 700.5 kilograms per meter cubed. Again, I'll let you review the solution at your own pace. Exercise 13, we're asked to consider a tank, as shown in the figure on the right hand side, that stores a quantity of acetic acid, which has a relative density of 1.08. There are 4 holes punched in a row at depths of 100 millimeters below the free surface, 200 millimeters, 300 millimeters, and 360 millimeters below the free surface, shown on the sketch. We're asked to calculate the pressure in the fluid at each of these depths. The question asks us to note the relationship found between the pressure and the respective depths. The answers for the various pressures are shown in the bracket here. Note that these answers relate to gauge pressure. Again, I would encourage you to stop the presentation, attempt exercise 13, but I'll show you the full solution on the following slides. So exercise 13, here's the solution. Drawn a small sketch for myself to illustrate the problem we have here, basically to calculate the pressures at A, B, C, D below the free surface, and we're given the respective heights in the question. Notice I've converted them straight away into meters here, and of course the question has stated the relative density of the fluid, acetic acid in this case is 1.08, so we need to determine the mass density of the fluid. So the 1.08 is relative to water density, so the actual mass density of the acetic acid is 1080 kilograms per meter cubed. Exercise 13, solution continued here. I'll let you review the solution at your own pace. It's essentially of applying the formula P is equal to rho GH at the 4 different heights from the free surface. Notice I've stated the answers in terms of pascals and also bar. Note for reference, the pressures vary linearly as a function of height h. Exercise 14, we've got to find the head h of mercury that corresponds to a pressure of 101.33 kilonewtons per meter squared. We're given the density of mercury is 13,600 kilograms per meter cubed. The answer is shown in the bracket here. Again, I'd encourage you to attempt exercise 14, but I'll show you the full work solution on the following slide. So exercise 14, here's the solution. I'll let you review this solution at your own pace. And here the solution does require a rearrangement of the equation P is equal to rho GH to find the head or the height h of the mercury. H is equal to 760 millimeters of mercury. And I'll leave you with some tutorial questions. Here's question 1a through to question 3a. Solutions here are very similar to that we reviewed in the exercises. Answers are stated in the brackets. Tutorial questions continued. Question 4a, question 5a. And read the questions carefully. Answered again, shown in the brackets. Question 6a, a rectangular tank, 5 meters by 4 meters, contains water to a depth of 3 meters and oil having a relative density of 0.75 to a depth of 2 meters. We're asked to calculate firstly the pressure on the base of the tank, secondly the total thrust on the base of the tank. I know that thrust in this context is actually the force on the base of the tank. And part 3, we've got to find the total thrust, total force on the longer side of the tank. Answers are shown in the bracket here. And here are a few hints related to question 6a. On the left hand side here shows a sketch of the tank. Notice that the oil floats on the water because the oil relative density of 0.75 is less than that of water, which would have a relative density of 1. Also notice the pressure distribution from the free surface to the base of the oil, and the pressure distribution here from the top of the water to the base of the tank. This pressure distribution helps us calculate the total pressure applied to the base and also calculating the various thrusts or forces applied to the tank. So firstly, to find the pressure on the base of the tank, we need to summate the pressures from firstly the oil and then from the water. So we're basically summating the ρgh values for oil and water. That will give the total pressure on the base. Part 2 of the question, we've got to find the thrust, essentially the force that's applied to the base of the tank. So the thrust, simple F here, on the base is simply the pressure on the base calculated from above multiplied by the area of the base. And the area of the base is 5 meters by 4 meters. The third part of the question is to calculate the thrust or the force on the longest side of the tank. Slightly more complicated here. The longest side of the tank will be this side, 5 meters by 5 meters. And essentially we're going to calculate the force applied to the tank side from the oil and the force applied to the tank side from the water. So considering the oil, we're going to evaluate the pressure at the midpoint of the oil storage on the tank. The oil, of course, will be on top of the water. So this is the midpoint of the oil. That relates to this point here on our pressure diagram. So the pressure halfway through the depth of the oil will be the ρgh divided by 2 for the oil. And then we'll multiply that by the area of the oil, which will be 5 times 2 meters. We next need to find the centroid of the water, which will be approximately here. So we need to calculate the value of this pressure here on our pressure distribution. So that pressure will be the pressure due to the oil, the ρgh of the oil, and now we'll add to that the ρgh divided by 2 for the water. We then multiply that by the area of the water, which will be 5 multiplied by 3 meters. So a slightly more complicated calculation for part 3 of question 6a. But hopefully the hints there will help you with your solution. And finally, question 7a, I'll leave that with you to review at your own pace. The answer is shown in the bracket here, in bar. And here's the bibliography used to help generate this presentation, which I hope has been of interest to you, and thank you for viewing.